Seems like we are going to be a small, dedicated audience today. Hello and welcome. My name is Mads Wilson, and I am from Copenhagen, Denmark. If any of you don't know where that is, I think if you go about 1,000 kilometers out towards New Zealand, then it's almost exactly on the opposite side of the Earth. So I have traveled quite far to get here today. I'm part of an organization called Copenhagen Suborbitals. Does any of you know about us? No? We are, to my knowledge, the only manned amateur space program in the world. We are working towards sending a human being into space and retrieving him or her safely afterwards. And we are doing this, let me check here. Sorry. We are working out of an old, one of the old buildings from the BMW shipyard in Copenhagen that was closed 30 years ago. And the image you see here is taken on the night where the Danish astronaut Andreas Mogensen was aboard the International Space Station. And the space station passing is the little line that you can see up here. As I said, we are trying to put a human into space. And when I say space, people sometimes think circumventing the globe or going to the moon or to the stars or something. What we are trying to do is basically the same as the Americans and Russians did back in the 50s. To get a human above the Kármán line, 100 kilometers, which is the official boundary to space, and back again. That's difficult enough. Going around the world, the globe, or to the moon, that is a whole different story. We will not go there. It will look something like this, and I will later get back to why we have chosen this particular shape and size of the capsule. But the idea is simply to send this payload up over 100 kilometers and making sure that it comes back safely. We have since 2010 launched 7 rockets already as different tests. You can see that we have a capsule over here. We have the Heat 1X, which was the first rocket we launched that turned out to be an extremely bad idea. I'll also come back to that later. And then we have some smaller ones that have served as technology demonstrators, and you can see the speaker rocket here. This is the one that we're working on at the moment. We are launching this from an area out in the Baltic Sea, or we have been launching. I'm very envious of what you have here in Australia, because as I understand it, you have a lot of nothing, right? You have a lot of empty space. In Europe, not so much. There's not really anywhere in Europe where you can safely launch a rocket, at least not if you don't want it to come down and hit something on the way down. And also the airspace is very, very densely packed with airplanes, of course, and it's very heavily regulated. So it's quite difficult. So 10 years ago, we found a loophole. And that loophole is called ESD 139. It is a military shooting area just outside the Danish island of Bornholm in the Baltic Sea. It was created sometime after the war, so that NATO could have military exercises where they could annoy the Russians, I guess, because it's close enough to Kaliningrad so that they can see everything on radar. But it's still in international waters, and it's still within EU, so it's far enough that NATO can say we have every right to be here. The good thing about this, when it's marked on a map at sea, that means that it is also marked on the maps for airplanes, and it is an unlimited height corridor, meaning that we have you only see half of it here. There's actually one more half up here. We have a square that goes all the way up to unlimited height, and it is like that because then the military can test missiles. But since it is in international waters, there is no exclusivity. So everyone can go there. So in principle, we can sail out with our rocket that looks like this in EST-139 and launch it, and nobody are able to do anything about it because it is in international waters, in principle. As you know, sometimes reality is a little bit more tricky because we don't, of course, we don't do this without telling anyone. We coordinate it with the air traffic control and with the Danish government and with all the countries surrounding the Baltic Sea, so that the Russians don't think that the crazy Danes are shooting missiles after them. Recently, we are re-evaluating, let me put it that way, our plans to launch from the Baltic. As the current situation is in Europe, it is not a very good idea. So we are looking at options in the North Sea instead. But this is how it looks. And when I said I was envious of all your nothing in Australia, it is mostly because launching from sea is very difficult. Imagine that you are standing on the platform doing something on the rocket and you forgot a wrench. Then you don't just go back to the workshop or to your toolbox or whatever and pick it up. You need to radio for a boat to pick you up, to go to some of the other vessels and hope that they have what you need, and then you need to go back. And sometimes, or some of the operations around launching the rocket, they are very time critical. So you cannot just take out half an hour to go and pick something up that you forgot. We are also very dependent on weather. It needs to be fairly good weather, no more than half a meter high waves, all the stuff like that. And we need, of course, also to keep to keep within the launch window that we have agreed with the air traffic, so that we make sure that there are no planes overhead. So it's quite an operation that, as you can see here, involves a lot of small boats. This here is our mission control vessel. And the small boats are bringing people back and forth, and we also have speedboats that sail out to the edge of the area to make sure that no leisure craft or anything comes in there. So it's, curiously enough, the big ships are never a problem, like the freight ships and oil tankers, because they have all the systems in place. They get all the warnings, they get everything, so they keep out. But it's all the little Mr. and Mrs. Hansen leisure boats with a sail that, and you would be surprised how long time it take for a sailboat to move just 10 miles out of that. We had one year where that almost destroyed the entire operation because it simply takes them too long to get out of the area. Our mission control is set up on the control ship, so we are controlling everything from there via, you can see the platform is over here, via radio. So it's quite an operation. And some of you might be thinking, putting a human in space, number one, why? Number two, that is not possible. We are working from the perspective of a principle that is, it just needs to be good enough. Because the way space flight and the whole space sector has moved the past 20 years is towards optimizing everything and squeezing those extra 10% out of an engine, because it is expensive to get payloads out. So they need, just a couple of kilos can easily get them a lot more value. We are going the other way around. We are saying, okay, a lot of the technology that we are working with is the same stuff that the Russians they used back in the Soviet Union, because they had the same approach. It doesn't matter if it's a little heavy or a little bulky or a little ugly. It needs to work, and it needs to work every time, and it needs to be just good enough. And just to put things in perspective, this is Starship. This is the Falcon 9. This is the Blue Origin thingy. I can't remember what it's called. And this is us. So you can see SpaceX was founded approximately at the same time that we were. That can make you a bit envious, really, but that's all a question about money. This is an animation I brought for you that shows how we envision the mission. All right, we are software armed. Rocket is in internal power.
Guidance navigation computer is armed.
I won't be the one sitting up there, by the way. Imagine sitting up there in that little can on the floating platform while waiting for the rocket to ignite.
Data is go. We are go for launch. Order sequence start. T-minus 30 seconds and counting. 5, 4, 3, 2, 1. Moving. Lift it. One time, feel it. We have main engine cut off. No turn off.
And that's it, really. The capsule splashes down in the water, and we sail over to retrieve it, and that's the mission. It will take about 15 minutes, give or take. Going up is not the dangerous or difficult part. The difficult part is not coming down. It will come down somehow. The difficult part is to make sure that we don't kill the payload, really, both going up and going down. When you lift something up, it accumulates energy, right? Because of the gravitation of the Earth. So all the energy we put into the capsule, sending it 100 kilometers up, when it comes down, that energy needs to go somewhere. And the only place the energy can go is into heat. Either in the heat shield, as you saw on the video in the bottom of the capsule, or as friction in the parachutes. So the most important thing coming down is that we can steer the capsule the correct way so that the heat shield is turned downwards and that the parachutes are upwards, and that we can control the descent so that the descent speed will gradually decrease, because if we hit the water with too high speed, that'll also be the end of the astronaut. So this is the mission. About 50 seconds of main engine, and then coasting up to 100 kilometers, releasing the capsule from the booster. The booster will come down in the parachute. It doesn't really matter if that hits the water, as long as it doesn't hit anything else. And then the capsule needs to come down in the parachutes. So those are the events. And remember what I said about killing the payload. When you're designing vehicles like this, then your number one design criteria is, how do we not kill, if it's a human or an animal, how do we not kill the person inside? And the first thing you need to think about is, what can the human body withstand? Fortunately, there has been done a lot of research by both the Americans and the Russians back in the day, and especially this series of tests have been used for almost everything related to speed and braking. This was done in the 50s by the American Army. They had some volunteers that put themselves on a rocket sleigh.
On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. He suffered no serious or permanent ill effects from the 55G peak deceleration load he took. Beading subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track.
It was later revealed that the part about not getting any serious or permanent damage was not entirely correct. There were some of them that it took them some years to recover after this. But luckily, we do not need to repeat these experiments to know what the human body can withstand. What they found out back then was more or less this. Acceleration from the back is bad, but not very bad. Forward acceleration, meaning that you are accelerated this way, is you can always do that unlimited. 20 Gs is not a problem. There's a little problem with your eyeballs because they are loose in your head, so they can move. But since they are moving backwards, there's something to stop them. So it's not so bad. Downward acceleration, which in our case is not very applicable because that would require you to stand on your head, right? Is not good. It's very bad. Upward, a little bit better, but still not good. If you're standing like this and being accelerated upwards, then all the blood will drain from your head and go into your legs, and that's a bad idea. And this is why the first rocket we did was a bad idea, because that was based on a stand-up capsule. We have some videos on our YouTube channel. You can see how that went. We killed the astronaut. We put a crash test dummy inside. We killed him, I think three or four times. We killed him going up, going down, hitting the water, and then he drowned afterwards. So that was not a good idea. So the reason why we have chosen, as I said before, that form of capsule is because every craft is designed according to the payload. The shape you know from the Apollo missions, that is called now an Apolloid, that shape. And that capsule is designed to accommodate 3 people lying on their back with their knees lifted and their arms like this, because that is the best position you can be in when you are being accelerated upwards. That is the way, the orientation of the body that can take most punishment. And that is why that capsule is designed that way. The next best thing is something called the Caspek position. And that is what the Russians have been using in the Soyuz capsules. And we will be doing something like that. That is sitting slightly leaned backwards so that you don't have any forces directly perpendicular on your spine. And you can still bend your arms and your knees so that all the blood is as close to your heart as possible. And then the head will be supported by something so that it doesn't rattle around. The best is, of course, if you can just lie down and so that the head will just be pushed backwards. And we have tested this. The minimum space needed is about 1 meter in diameter to do this. Of course, I mean, a jockey would be perfect. You cannot be too big, you cannot be too heavy, and you need to be reasonably fit. But otherwise, there are no real requirements because you won't steer anything. It'll be the computer who does everything. So your only job as an astronaut is not to die, really. And we have tried. We have tried several configurations. Where did it go? Something with the computer. We have tried several configurations, and we ended up with something in the order of 955 millimeters in diameter. And the reason for that weird measurement is because that is the measurement you get when you take a standard size steel plate and round it up and weld it. Which again makes everything a lot cheaper, because then we don't need any special cuttings or special orders. We can use something that just comes on a pallet. That is what is needed anyway. 1 second, I need to check. It looks like I don't have any power on the computer up here. Let's see. Okay, so what can possibly go wrong? The answer is, of course, quite a lot. We launched the first Heat 1X rocket, and that was not a good idea. As I said, we killed the astronaut numerous times, and also it was slightly banana-shaped, so it didn't fly straight. It had no active guidance, meaning it just flew wherever it wanted to go. Guidance of a rocket is one of the most important things at all, because you need it to point in the right direction all the time, right? Does any of you play dart? Dart is a good example of rocket guidance, really, or shooting an arrow. You need something that is heavy in the end, or heavy in the direction that the arrow is flying, and then you need drag at the end of it to make sure that it stabilizes. You can do that with a rocket also. That's why rockets have fins, because that creates drag. The problem with drag is it only works in the lower part of the atmosphere up to about 8 or 10 kilometers. Then there's no air, and you cannot create the drag anymore. So you need to be able to guide the rocket in some other way. And after the first launch of the Heat 1X, we devised a guidance system, and we thought, okay, we don't need to do testing really. We can just build a very, very big rocket. We don't even need to test all the elements of it. We will just build it, and then we will put it up on a test stand, strap it down, fire it, and then do an all-up test as the first test. And this is how that went.
5, 4.
What you can see on this video is the rocket. Right now, the engine is in what we call pre-stage. You cannot just ignite a rocket engine. You need to ignite it slowly or softly first, and then ramp up. So right now, the flame is flickering it because it's in pre-stage. There, it shifted to main stage, and I don't know if you noticed, but there was a little rupture here, meaning that all the fuel came out in about 5 seconds, being fed by pure oxygen that just slowly poured out. There was so much atmosphere, so much oxygen in the atmosphere that everything burned. The aluminum fins on the rocket burned. The only reason we have this footage is because we had strapped a little GoPro with cable ties about 1 meter from the engine, and it got so hot that the cable ties melted. And then the camera fell down into the flame pit and landed and cooled down in the water. And then afterwards, we took it apart very carefully, took the memory chip out of it, and there was still this footage left on it. You can see it was in pretty bad shape. And that was about 2 years of work that just went up in flames in 30 seconds. And the fun thing about this project is when something like this happens, most people will be like, oh, fuck this shit. But I remember that day we were standing in the bunker and it just smelled like vodka everywhere. We use ethanol as fuel. And for the first minute or so, people were like, and then you could see the look on people's faces And I knew that they all of them were thinking, okay, let's go build another one. But this time we looked at ourselves and each other and said, okay, we need to do this differently. We need to take a different approach. We need to be a little more systematic. So we created 2 test vehicles, Nexus 1 and Nexus 2, that were supposed to be launched in the following years. And the reason we did that, went small, is because the only thing that you cannot really scale up on a rocket is the engine. Everything else is the same. All the systems, all the communications, the guidance, everything. It's the same. It is only the engine that you cannot scale up. And it's far easier and far cheaper to build smaller rockets. And then the systems developed, all the communications and guidance and steering and everything can just be reused because it's the same software, more or less. You just need to put in different parameters. So we ordered this IKEA rocket set. This is all the elements needed to build the 2 rockets, and started building. Of course, we also did a lot of engine tests. I skipped that part. That took about a year, where we tested the engine 30 times to make sure that it worked. I think this is a little bit funny, but it is also true. And the weird thing about all this is, when you think about rocketry and launching rockets, what do you think is the most difficult part? It's not the engine. It's not all the details. It's not all the technicality. The most difficult part in launching a rocket is to make sure that the pointy end is up. And I'm not kidding you. Of course, the pointy end is always up when you're launching it. But once it flies and you have guidance on it, then it is surprisingly difficult. Because how do you know? The only way you can know is by putting a gyroscope and a magnetometer, for example, in it. But gyroscopes, they drift. They are not very precise over a long time. You can buy very precise gyroscopes if you are the United States Army and or have shitloads of money. But gyros obtainable by normal people are very, at least for this purpose, very bad. Luckily, then, 20 years ago, along came the smartphones, and that boosted development in small MIMPs, magnetic gyros, and they have gone increasingly better over the years. So the ones that you can get now are surprisingly good. So that's one thing, keeping the pointy end up. The other thing is you need to control the combustion. You need to control what comes out of the engine and at what speed. And then you need to use that somehow to steer the engine the correct way. And this is the gyro from the Apollo rockets that cost. I don't even think that the NASA knows what they cost, because they built them back then. They invented them, more or less. So it's probably millions or billions of dollars. This is a analog device airplane gyro that cost about $5,000, and that's adequate. Of course, there's a lot of razzle-dazzle and a lot of details, and you need to calibrate it and all that. But it works for the purpose of a flight where you have engine power for 50 seconds or even 90 seconds. It works. After a couple of minutes, it starts getting confused and doesn't know where it is and all that. But otherwise, it works. The next thing you need is something to control it, a computer, right? If we go all the way back to the V2 rockets, they didn't have a computer, but they had gyros. All those gyros, they were analog. And analog gyros or analog control is, in some sense, it is only in recent years that we have computers that are fast enough to do the same as an analog gyro could do, because an analog gyro is extremely fast. but it is also mechanical, and everything is a coupled system. So you cannot just reprogram it. Then you need to redesign it, right? It is easier with the computer, but you don't just use any computer. When people think space flight, or at least within the past few years, most of them think about SpaceX, right? Landing the rockets and all that. From a physics point of view, that is insanely difficult, and it requires an enormous amount of computing power. But to balance something going up like this, not so much really. You need a small CPU that can. An Arduino really could do it. You don't need more than that. The trick is that modern computers, probably what most of you are working on, you are working on a level probably up here, or maybe even higher. Maybe you're doing Java, that is an interpreter on top of the operating system, or maybe you are working in here where you're using Java on a virtual machine that is actually a software representation of a hardware set. You know what I mean? In all these layers, there's a lot of stuff that could go wrong, and a lot of the power, the computing power, are consumed on doing something else than what you need to do, adding 2 and 2 and whatnot. But if you work with the embedded computers, then you work here, and you can do the basic instructions directly on the hardware. Of course, the problem is then you don't have an operating system. You don't have anything to time anything. The Apollo computer had a 2 megahertz system clock. Actually, it was only a 1 megahertz system clock because that was just the main clock. And then it was divided down by 2 16-bit architecture and 72 kilobytes of program memory. That's it. That was what flew the Apollo missions. That had all the code in it for all the steps of the mission. Well, there were 2 computers, so not all of it, but almost. This is the Arduino Duo. That cost what? $50. And this is what we have been using. The speed is relevant. It could have been done with 8 megahertz. It doesn't matter. And the only reason why we have chosen this one and not a Mega, for example, that runs the 16 megahertz is because of the 32-bit architecture. Because floating point arithmetics from the IMU and the gyros comes out in 32 bits. So it doesn't take four cycles every time. It can do all the additions in one cycle. But that's it. And most of the time, this computer is not doing anything. It's just waiting. And operating system, we don't use that. We have designed the architecture different. What we have done is we have said, okay, every task has its own computer. And then those computers are talking to each other. So that the engine controller runs on its own computer and has a control loop that just keeps track of what the engine is doing. The guidance system, the GPS system, and the communication system all have their own computer. So they're just running in parallel. That also have the advantage if one of them breaks down, it doesn't affect the other ones. They're still running. And it's cheap. And by using the same architecture all over for everything, then we can also use the same compilers, we use the same debugging, and we know that it has been tested. Of course, we cannot use the Arduino just out of the box with little wires and pins in it. We have designed a bit more rugged version, but it is essentially the same, just with more breakouts and a redundant power supply, and we have designed our own breakout board so that the engine controller can have its interfaces to pressure sensors and whatnot, and the guidance computer can have its IMU. This is also because the computer needs to be able to withstand a lot of stuff. This is the engine controller close to the oxygen tank. It gets to about, even at this distance, it gets to about minus 50 Celsius, and it needs to be able to handle that. So You can see this is what I'm talking about. This was the architecture of the next rocket and will be the architecture of all the future rockets. We have the IMU, which is its own computer, the GPS controller that takes down data for two or three GPSs, the engine controller. Then we have a data link controller that communicates with the radio, receiving and sending messages. And then we have a separate system that has nothing to do with the control and guidance, with a couple of cameras so that we can send a live video feed down from the rocket. The radio system is interesting here because I don't know what, obviously I don't know what any of you do, but in normal day work, even if you're working in a bank or whatever, we have gotten used to extreme amounts of data. Even when we do testing, we dump all sorts of, and we don't think about it because it doesn't really matter. Hard drives are big, bandwidth is big. You can just send error messages as you want to or dump data. When you are working with a radio up and down link, that's just not possible. So you need to limit yourself to only what is needed. And this also comes back to the just good enough, because the data exchanged by these systems here, this is the example of the data format from the GPS system. It doesn't need to be more than this. We are not even declaring it as strings or using directly integers. It is simply just an array of bytes, just like when you're old school programming in C, where you know from position 7 to position 10, that is the timestamp, 4 bytes, like that. And in this case, we have 36 bytes of data that we send over the radio link. And it goes like this. You don't need much bandwidth. It can be taken down either from one of the other systems that needs the data, or from the base station. We send data down 10 times every second on the radio, and then the rest of it we log on memory modules inside each computer at 100 hertz, so 100 times per second, so that we know that even if we lose the rocket, we have most of the data, and if we find and retrieve the rocket, then we can take out the memory modules, and then we have a much higher resolution. But it's not really needed for the purpose. I don't know if any of you knows about radio. I just brought this to talk about it. But the more information you're sending, the more bandwidth you need, and the longer or the further away the two stations are apart, the higher power you need to get over the noise floor, and so that they can hear each other. But the more you can limit the information sent, the more you can also narrow down the bandwidth, and that makes it a lot easier to hear the two stations. In theory, unlimited time gives unlimited signal to noise ratio. You can think about it like this is from a spectrum analyzer. You can think, if you think of this as the noise floor, and this is the signals. But think of it like, if this was all noise, then a 1 second transmission, you wouldn't be able to see it because it would just disappear in the noise. But if you had a 1 hour transmission where a 1 was 1 hour and a 0 was 1 hour, then even with a very high level of noise, you would be able to see the pattern, because noise is random, right? So you would be able to see the pattern. So the more time you have, the lower signal you need. So that is why we are limiting the bandwidth as much as possible. And that's also happened a lot in the past 10 or 15 years. I don't know if any of you know about this, but this we use extensively. It's a little chip that has been developed to receive digital television. And of course, someone has found out how to build something else around it, and you can buy this little thingy. I think it cost $30 or something. And this is a complete spectrum analyzer for radio signals. You can buy it and play with it. You can receive everything. You can receive airplane traffic. You can whatever you want. Okay. Nextria 1 systems demonstrator. We have all the technology in place. Everything is assembled. We have designed the new systems. In 2015, we were supposed to launch, and we got a little bit of nerves because just a week before launch or something, Andreas was on the International Space Station, the Danish astronaut, and he sent down this. Good luck, guys. Talk about pressure, right? But unfortunately, we didn't launch in the summer of 2015. There were some forest fires in Sweden, and we had to skip the launch campaign. That is the official story. The correct story is that we were not ready. We were there, but we were not ready. But the year after, we succeeded. We had some beautiful days at the end of the summer, and we launched Nextria 1. And remember, this rocket was all about testing the events that you saw before.
We are losing power.
Spoiler, this was not supposed to happen.
This is Fido here. I have no altitude on the rocket.
Ja, vi kommer ikke så. Der er ingen bog. Der er ikke.
We have a rocket in free fall. The parachute is very down.
It sounded like that. It is my slightly nervous voice you can hear on the radio. It sounded just like that when it came down. What happened here was that it ran out of fuel. And then you're probably thinking, how the hell can a rocket run out of fuel? Haven't you measured how much you put in it? Yes, we did. But when you have combustion in a rocket engine, the pressure inside inside the engine pushes outwards, but it also creates a counter pressure towards the injector and towards the fuel tanks. If the oxygen to fuel ratio is off, then you get either a lean combustion or fat combustion. And that creates a wrong pressure in the engine. That wrong pressure then creates a wrong counter pressure against the tanks, which means that either the fuel or the oxidizer or both will come out of the tanks at a wrong speed. That again creates an even worse combustion. And then the rocket runs out of fuel because it burns it too fast. The Nextria 1 the engine was controlled by a system called pressure blowdown. Basically, you have a tank and then you pressurize it and then you open a valve just like a balloon, and then or water rocket, and then the fuel comes out. The problem with it's a very simple system. The problem with that system is that nowhere on the pressure curve do you have the optimal combustion. Well, at one point you have, but it is either too rich or too lean. What you do is you design around that so that you know that you have a too high pressure in the beginning and too low pressure at the end of the flight, but it doesn't take much to get all to be very very wrong, and you cannot really do anything to fix it. You can see this is the rocket after retrieval. All the dents that we have in it is because of the water pressure. It went down about 50 meters under the surface and just buckled up. And the only reason why it's floating is because it was filled with the styrofoam in all the cavities. You can see all the remains floating around here. And the bubbling is pure oxygen just bubbling out of it. But we got some really good data out of it.
T-minus 10 seconds.
This is the data that was recorded by the onboard computer, and this can give you a little bit of a
Ignition.
idea about how this works. You can see, for example, we have an average G load of 12. That's quite a lot. And here the engine cuts off. And but the rocket is continuing and nothing happens. The parachute doesn't come out. And why it did this is because
This is Fido here. I have no altitude on the rocket.
the IMU saw that the engine pressure dropped. And then it said, okay, but I'm not at the end of the flight yet. So that must be a sensor malfunction. I'll just continue. And then when our flight director pressed the parachute out button, that was error number 2. Someone forgot that when you have a machine like that are dependent on states, you cannot jump a stage. So when he pressed the parachute button, it should have said, okay, nose cone off, then parachute, but it went directly to parachute. So on the IMU data, you can just see where the gas generator inside just went off and nothing really happened, and then it just came down, and we couldn't do anything about it. Yeah, let's see. It's pretty beaten up. When we launch Nexio 2, I won't go into details with that because it is essentially the same story, and it's quite boring because everything worked. You can go to our website or YouTube channel and see the videos if you want. But that Nexio 2 worked beautifully. Everything went as it should. It came down in the parachute. We retrieved it. All the electronics are fried because of the salt water, but in principle, we could clean it up and use it again. And then this class of rockets are not really interesting anymore because we have all the stuff we need. But the thing about this rocketry is that it is at least 80% other stuff. Most of the time we spend on this project is not spent on building rockets. It's all the stuff around it. Remember, you saw all the ships and all that. It is a huge operation with a huge amount of maintenance. We have our organization looks like this. We have a board the board is elected every year among the members. We have a support group that's what pays the bills, or that's how we try to pay the bills, because of course this is costly and we don't have much money. And then we have all the subgroups underneath that are responsible for planning, building, maintaining, and all that. About every year we have a seminar where we exchange knowledge. The way this works is we don't have a Elon Musk that is pointing and saying we need to do this and we need to go in this direction. What we do is every year we sit down and we have a discussion, and then it is decided by consensus what we should do. And then it is the board's job to make sure that we move that way. But it is done by consensus. That can also be tricky sometimes. I don't know if any of you know or have experienced that at work, but highly skilled nerds are not usually the most socially apt people. And for some reason, it also tends to that their missing social skills are not the same, so they can clash in ways that you can't even think of. So, but we have people working on CFD modeling, for example, and modeling structural integrity of metals. This is we got some licenses for some software sponsored a few years back, and this has really helped us so that we can model and see what will happen. We have done over the years a lot of engine tests, and that also costs money and takes time. You need to build a test infrastructure, and you need to. I mean, we consume about 500 or 600 liters of liquid oxygen every time we do this, and that also costs money and takes time. This is an example of this is a machine we built to weld the inside of tanks, and sometimes progress is also slowed down because we need to build a machine to build the machine to build the stuff we need to build. So when you don't have money, then you can only spend time, right? And build stuff. And I must admit that sometimes we also get caught up in rabbit holes, because that is also what engineers do. That they find something that is really interesting, but not really in the right direction. Parachutes is another good example. This is a place called Copenhagen Air Experience. It's a leisure place. You can go and float on air in this tunnel, and they lend it to us sometimes, and then we can simulate an air tunnel to test capsules and drag, for example. Parachutes is a big thing. We do a lot of. There's one coming up. We do a lot of parachute tests because we need to build our own parachutes for the rockets, because you can't really buy stuff. Well, you probably could, but it would be very expensive. So we have a couple of guys that sews these parachutes. And there's a weird thing, or a curious law in Europe, that you cannot test a self-made prototype parachute by dropping a sack of potatoes out of a plane. You can only legally test a parachute if someone uses it. And that is quite challenging sometimes. So this is Ahmed here, parachute instructor that helps us sometimes testing our balut. So what they need to do is they need to go up with the plane, jump out, test our parachute, release that, and then land in their own parachute, and then spend the rest of the day looking for that parachute somewhere in a wheat field somewhere, because it never lands where you want it to. The same with this one. This is him testing the 3 parachutes for the capsule. Same story. It would be a lot easier if we could just drop something in the parachute, but that is not legal. There's a lot of other testing involved also. This picture here is where we are testing a capsule seat prototype in an autoclave. We bought this a few years back. I don't know if you know autoclaves. They're used sometimes to harden fiberglass, for example, where you can heat them up either put them under pressure or under vacuum. We bought one of those surplus and use it as a vacuum chamber. It works fantastically. And then, of course, as I said, the support group, someone has to pay for all this. The way we do that is either by doing what I'm doing now, or by making videos and other content where people all over the world can see what we are doing, be inspired by what we are doing, and then hopefully they sign up as support members and pay a little bit of money every month. And that is how we fund the project. We have currently about 500 support members paying anywhere from $5 to $20 a month. And that's what we use to pay rent and materials. And it is not nearly enough, but we get by. And then when we do launches, we also do video coverage. Remember, I said we had video cameras on the rocket. We don't really need that for a scientific purpose. It doesn't really matter. We most likely know how it would look, right? But it is important for the people supporting us to be able to see what's going on. And when we started this whole operation, that was before Starlink. That was before anything. We couldn't afford a satellite. So we had to develop our own transmission system. And we have a guy called Peter who has written a piece of software called Snowmix. It is on GitHub if anyone wants to play with it. It is the only part of this project that is true open source. Rocketry cannot be open source for obvious reasons. You don't want a guidance system floating around on GitHub. But we have had inquiries from shady countries and Palestinian water drilling companies and stuff like that wanted a guidance system for a rocket. But for obvious reasons, that's a bad idea. That will very quickly send you to Guantanamo. Peter wrote the software mixer. that we can use to control the cameras 30 kilometers out to sea. What you see here on top of the boat, that is the Wi-Fi transmitter. Yes, this is Wi-Fi. We have modified some standard Wi-Fi equipment, and then we have placed a receiver on top of the old military listening post on the island of Bornholm, and those two are then aligned with each other, and we are able to make, I think, 25 or 30 megabit connection from shore to the ship when it works. The first year we launched and had this system, I was sitting in a car down here, manually steering the antenna, because Peter, who wrote the software, he did it overnight while sailing to Bornholm after he hadn't slept for 3 days, and he accidentally wrote the software in such a way that it thought that the island was spinning. So he didn't guide the two antennas to each other. He wrote it so that the whole island was spinning, which created some strange problems. So I had to sit and look at the AIS data from the boat, and then manually control the antenna and point it in the correct direction. This is the mission, the video control, where he is sitting, Peter, and then controlling and mixing all the video cameras on the boat on shore, and then sending it to YouTube. And I think we have a delay of a minute or something. That's pretty good, I think. Then, of course, there's a lot of software. This is our FIDO system, where we can see where the rocket is and where it will predict where it will land and all that. That also needs to be maintained. And then we have all the marine stuff. I mean, who thought when they went into amateur rocketry that they would be wearing a yellow jumpsuit and scraping shit off an old North Sea trawler? But that also has to be done, right? Because when you own a ship, you need to maintain it. So a lot of the time are spent on all weird other things that has nothing to do with the rocketry. But we are hopefully getting there. This is a timeline as it looks so far. We haven't launched anything since 2018, partly because of COVID and partly now because of the Ukraine thing. We are building the speaker. Hopefully, the prototype will be launched within a couple of years, but nobody really knows. Right now, it mostly depends on funding, really. On that note, you are more than welcome to go into our website and see what we have, and maybe sign up if you are interested. Yeah. Any questions? There are so many rabbit holes in this. Yeah. That's a very good question. Yes, in principle. As long as we keep, I think it's about 70 or 80 kilometers. That is not, the problem is not so big, and it also depends on the solar flares and stuff like that. But yes, in principle we do, because just one stray particle that. Yeah, precisely that. Then the CPU resets or data is corrupted or anything. That is also one of the reasons why we are using separate CPUs for the different systems. We haven't tested it, but number one, you can buy military-grade versions of the Admiral CPUs that are radiation hardened. They are expensive, but they are not that expensive. But you can also come a long way just by shielding it with making sure that everything is metal enclosures and stuff like that. But I think the best thing would be to use the radiation hardened CPUs. Yeah. It's mostly when you're using satellites you need to think about it, that are exposed all the time. Yeah. Yes? Yeah. That's a load issue, really. One parachute is enough to carry the next year rocket that only weighs a couple of 100 kilos, 150 kilos. But when you have a bigger capsule, then you also need bigger parachutes. And it is also because let's say that you have a capsule and one big parachute. Like the US military, they have some that they use to drop tanks, for example, unmanned tanks. They drop them from an altitude where they don't need to brake. They don't acquire enough speed. They don't need to brake so much, so they can just drop them and unfold the parachute. But when you're coming down from 100 kilometers, then you need to brake slowly. So what you do is you reef the parachutes, and it's better to have many smaller parachutes than one big parachute. Then you reef them, meaning that you don't do a full unfold to begin with. You reef them, then you brake, and then there's a little line cutter that cuts the reefing line, and then the parachute fully open. So you brake slowly, and you also have redundancy. Should one parachute go, it won't be as big as a disaster as if you only had one and that had a hole in it or something. Yeah. Yeah. Anything else? Otherwise, you are welcome to approach me later. I'll be here all day. Thank you so much.